Tonight's video is on section 2.1, the derivative and the tangent line problem. Homework is section 2.1, 1 through 4, 7, 10, 13, 19, 24, 28, 30 through 32. So we're going to review what you already know from Algebra 1. So I graphed a line, and I put it in slope-intercept form, y equals mx plus b, in which m is the slope of the line. And so we could find the slope of the line if I had 2 points, and so I would take those 2 points and do the difference between the y's and the difference between the x's. So y2 minus y1 over x2 minus x1. In other words, this would be the rise, and this would be the run. The rise, the change in y's, the run, the change in x's. The slope is the same everywhere on the given line. On any straight line, the slope is all the same no matter what 2 points that you pick. So that's what we know. So let's see here. Let's cover this up a little bit, like so. So now what I did is I sketched out just a curve, something that is not a straight line. And I picked out 2 points. So this point here, I'm going to call it x1, and then the output would be f of x1, right? Because when I put in x1, what is the y? This point here, I'm going to call it x2, so this would be f of x2, or the y component. And then the difference between x1 and x2, we're just going to call it the change of x. What is the change? Is the change by 3? Maybe this is a 2 and this is a 5. Maybe this is a 7, this is a 10. Just what is this distance, or the change of x? So let's say, we don't know how to do the slope of a curve, but I could pick out these 2 points. And any 2 points, I could draw a straight line through it, and this has the same slope everywhere. So I could find the slope of a secant line, 2 points that live on F. And so the slope of the secant line, well, this is still y2 minus y1 all over x2 minus x1. I just didn't call them y's this time, but we know a y is f of x. Sorry about this. So another way I want to write this, it's still the same thing. y2 minus y1 over x2 minus x1. I kept this the same, still the slope of the secant line. But instead of calling this x2, can't I call this x1 plus the change of x? Like if this was 7 and this is 10, another way to say 10 is 7 plus 3. So I just wrote this y output and this x something else. x1 plus change of x. So again, this is just really f of x of 2. F of x1 plus change of x minus f of x of 1 all over x2 minus x1. All we did. And really, the distance, or when I subtract these two, isn't that the distance? Couldn't I replace this by change of x? And this is something I'm going to use here. So it all came from slope. This is really y2 minus y1 over x2 minus x1. That's just the difference after I did the subtraction. That's the change of x. So now, I'm going to use the same thing here. I'm just going to change it up slightly. Now I'm going to talk about a tangent line. Well, if you remember from geometry, take a circle, and that is tangent to the circle because it intersects it at only one value. The moment I do this, that's a secant line. Right? It intersects the circle in 2 places. So my tangent line, what I really want to do is I want to have a tangent line at this point right here. That's the x value, c, some number, and then the output is f of c, right, the xy. So this is about the tangent line. So I'm going to set this up. I'm going to call this c. I'm going to call this change of x, because it's like x1. So this would be c plus change of x. So this is f of c. This is f of c plus change of x. That's what I'm calling this. So what tangent line? What I really want to do is we, on the last drawing, had a secant line, right? Because I don't know what the slope of this curve is. So I could find any 2 points to find the slope of that line. But what if I want to find the slope only at this 1 point on this curve? So it's like taking it and scooting backwards. I'm going to keep scooting backwards. I'm getting closer and closer. So look at, I'm still going through here, but this dot's going to here. It's going to here. Let me scoot back a little bit more. It's going to here. So what I really want is I want to figure out where my pin will curve around and intersect it at one place. So probably the tangent line is about like so. I just want to find the slope at this 1 point to that curve. In other words, take my pin and roll it around. When I get to that point, I want to find the slope of this tangent line. The tangent line, that intersection right there at this point between the tangent line and this curve. Where does it intersect it at one place, not at 2 points? So I have this equation. The slope of the tangent line is the limit, right? As this delta x goes to 0, because I keep bringing it back, and I want the change of x to go to nothing. I want to go all the way back to the c. That's what I did. I scooted closer and closer and closer until I got to the tangent line. It was secant line, secant line, secant line, secant line, secant line, until I got to only here. My pencil only intersected there. So the limit, here's the same thing. This is y2 minus y1 over x2 minus x1. x2 minus x1. Right, so this is the slope. This minus this, all over this minus this. That's the slope of the tangent line, but it's the limit definition. I have to get closer as I'm approaching 0, as that distance goes to nothing. So let's start cleaning that up. In other words, I could cancel out my c and negative c. That goes to 0. So I'm going to leave it generic. I'm not going to do a specific example quite yet. So this is important. M is the slope of the tangent line, to the graph of f, this is f, at the point, at this point right here, c, f of c. That's what this is. This slope is the slope of the tangent line to the graph of f at the point c, f of c. At the point maybe 1, 2, or 3, 5, or negative 1, 4. So I'm going to give you all the notes, and then we're going to start doing a couple of problems. But I'm still not done. Sorry, there's a lot of notes today, but they do all tie together. So that last one was to find the slope at a particular point on this function. That's this equation. At that particular x value, c. The definition of the derivative of a function, which is calculus, this is where I'm changing over to calculus now. The derivative of f at x is given by, look at, isn't it the same equation I just had? But what I called this was the slope of the tangent line. Oh, but wait, it's a little different. Instead of c's, I have x's here. This means the first derivative or the derivative of. First derivative or the derivative of. When I write this, I'm going to say second derivative. When I write this, I'm going to say third derivative, but not today. So I can say the first derivative or the derivative of what? Of my f function. Here it is. Well, what does that mean? Well, the last one had a c at a very particular point. Now this is going to be an equation for the slope of the tangent line to the graph of f at any point on f. On any point. For any point I want to choose. I'll let you write that in just a moment. In other words, when I find the first derivative, right, this is going to be the slope at any point because it's going to give me an equation. So I can find the slope here. I can find the slope here. I can find the slope here. Of what? Of the tangent line to the graph at a point. But when I take the first derivative, it's a generic equation for any x value. Again, this is going to be an equation. What is the slope? The slope. This is going to be an equation for the slope of what? The tangent line to the graph of f at any point on f. That's the only difference between the derivative and for the slope of the tangent line, it just happens to be at a particular point. I don't need to find it generically. I just want to know the slope here. It's going to be a negative slope. Well, now that I've found the slope for this tangent line, let's make an equation for this tangent line to the graph of f at the given point. In other words, I know it's a cute little picture here, but here's this and here's this picture here of f. I picked a point right here, we'll call it x1, y1, and it curves up and around, so the tangent line looks like it might be, well actually I think it's down a little bit further. I think the tangent line looks more like this. I don't think I did a good job. Where would the pencil be? So I think I like it right here. This is the tangent line. So what I just found is I just found the slope of the tangent line, right? The slope of it. But what if I want the equation, or the y equals mx plus b, the name of this whole line? Right now all I have is the slope. I found the slope of the tangent line. How did I do that? I did that with this equation at a particular value. So once I have the slope, well, I'm doing point slope form. This is y minus y1 equals slope times the quantity x minus x1. This, after you add the y1 and distribute this through, you're going to get the slope-intercept form, which you're used to. But in point slope form, all I need to know is a point that lives on the line and the slope of it. Well, I already have the slope. Put it here. All I need is one point. Well, this point lives on this f function, and this point lives on this tangent line. So I'm going to take that point x1, y1 and put it here and here. Now I have the equation. I have to do it again, distribute and add that y1. I will get the equation of that line. I don't know, I'm going to guess right now that that line is going to be something like y equals, because I can intersect it at about 4. The slope is negative 1/2 x plus 4. Intersect at 4, and it's a negative slope, down 1 over 2, down 1 over 2. I don't know, just a stab in the dark. So let's try ourselves a problem. I took the directions right out of the textbook. Here's the directions. Find the slope, not the equation, find just the slope of the tangent line to the graph at the given point. It means I'm going to use this equation. Find the slope of the tangent line because it's going to be at a point, at this point. Okay. So there's my equation. This is what point it's going to be at. So the slope of the tangent line equals the limit. So the change of x goes to 0. I'm going to write it generically first. That is the equation. Well, I guess I should call this guy f here. So now what I'm going to do is I'm going to take this f function, wherever I see x, I'm going to drop in a delta x plus x. So here's this, took the x, right? So that is this piece here, minus just f of x the way it's written. Okay, f of x just the way it's written. So here's delta x, here's x squared minus 4, putting in the delta x plus x, minus x squared minus 4, all over what? Just delta x. Now I'm done looking up here. Now I just have to do math. So let's see, what does that mean? Delta x plus x times delta x plus x minus 4 minus x squared plus 4 all over delta x. Now, see, I still use the generic again. So what I just noticed that I'm doing is I'm actually doing this, which is still the slope. I'm just doing it generically. I left it with an x instead of putting in the c, my 1. So I could have went ahead and done the slope of the tangent line, and instead of x, putting in a 1. Sorry about that. Delta x squared plus 2 of these x delta x's plus x squared minus 4 minus x squared plus 4. Oh, wait. Let's see if I can cancel something. So I need to get rid of this because I can't take that limit, but I could take a delta x out of both. Put in 0 for delta x. There's my generic equation. Why? Because I found the generic. I took the first derivative. Now I said at what? What point was that? At 1, negative 3. At 1, negative 3. So what I want to know is at 1, negative 3, I want to put in the x value, right? Because that's my c, my x value. So equals 2 times 1. There it is, the slope of the tangent line. Yes, I've already done this problem. I wanted to go ahead and do it live in front of you. I did one more thing. X squared minus 4, isn't that a parabola vertically shifted down 4 units? I sketched it out. 1, 2, 3, 4, over 1, up 1, over 2, up 4, over 1, up 1, over 2, up 4. At 1, negative 3, at 1, negative 3. That is a point that clearly lives on my parabola. What I wanted to find is the slope of the tangent line to the graph at the point, what? 1, negative 3. The graph of what? Here's this graph. So here is my tangent line, right? See, take my pencil and roll around my parabola, right? But right here is where I want to figure out what the slope is, right here. And we figured out the slope to be 2, right? The slope is 2, which means I go up 2 over 1, up 2 over 1. That looks like that's true. In fact, let's do one better. Let's find the equation of this line. I know the slope of this tangent line equals 2, right? The tangent line is equal to 2, because I just found that out. But let's go ahead and let's find the equation for the tangent line. So I'm going to use the point slope formula. I just found the slope. I'm going to drop that in. At what point? At 1, negative 3. This point right here lives on the curve and on the tangent line. It's the point of intersection. So this x value goes here, this y value goes here. Now I'm just going to distribute and subtract 3, combine like terms, and there is the equation of the tangent line. That's y equals 2x minus 5. Y equals 2x minus 5. Let's see. Y equals 2x minus 5. So how do we graph that? We go down to -5. 1, 2, 3, 4. Well, it's probably -5. And then we go up 2 over 1, up 2 over 1, up 2 over 1. Oh, yeah, that is the equation of the tangent line. Yes, I won't do this on another sheet of paper. I'm almost done. Last problem. Plus, remember, you get to do all these in class anyways. Now it just says find the derivative. That's what I just did. It means find this. See how it says at no point? I'm going to find the slope of the tangent line to the graph of f for any x value. That's what first derivative means. Okay, let's do that. So first I'm going to write this again so I remember it. The first derivative x equals the limit. Here's this equation again. Sorry, that's delta x. So substitute. Oh, let me bring this back down, sorry. So wherever I see an x, I'm going to make a parenthesis and put in my delta x plus x. So 2 times the quantity delta x plus x squared plus delta x plus x minus 1. That's just this piece. Minus, just go and get f of x just the way it's written, but remember to put parentheses or brackets around it. Now I'm ready just to look at this piece. And again, see, here's my problem. I put 0 in the denominator. I cannot find the limit. It means I have to do all this math and hopefully find a factor of delta x so I can cancel it out. So I can finally find my limit, which is now what I'm finding is the slope, the first derivative, the slope of the tangent line. So one more time. This means this times this plus, well, I just take out the parentheses, minus 1, distributed the negative, all over delta x. Well, now I better do this math. Turns out here, delta x times delta x squared. There are 2 of these, x squared. And so I clean this up. Let's see what I have. This and this. That's it. I have the delta x and the minus 2x squared. That's where I got that from. Next. Well, now I just distribute the 2 to all 3 terms. Well, let's see what I did up here. I have all terms up in the numerator. So let's see here. Negative 2x squared, positive 2x squared. That's it. So I need this gone, but there's a delta x in this term, and this term, and this term. So let's factor them out, which is what I did. Because I got to stay focused on what I need. I need to find the limit. So these 2 cancel. And so then I'm going to take the limit, now that I can cancel this. Where does the 0 go? For delta x. So 2 times 0 is 0. I'm just left with 4x plus 1. What is this? This is the slope of the tangent line to the graph of f at any point. This is the slope of the tangent line to the graph of f at any point on f. And that is it. Thank you.